Let's take a look at the problem from yesterday. We had a pool and it was a hemisphere with a radius of 12 meters and it had water in it to a depth of 10 meters. Then, and it was also oriented with the round side down, like a sensible person would build a pool. Then for this problem, we said we don't actually have to build this pool. So what we're going to do is we're going to seal it off, seal all the water in, and then invert it. Anybody who asks, how would we possibly do that? I'd be like, well, I don't know. I'm not an engineer. I'm just sitting here trying to write math problems that I find kind of interesting. So the problem is to invert our pool and then find the new depth of the water. Find the depth of the water in the pool, in the inverted pool. I also said, show your calculations and round your answers to 3 significant figures. So what we want to do is not a bunch of work that we've already done. So if you recall from yesterday, we calculated the volume of water and that part hasn't changed. So the volume of the water hasn't changed. Also, the way that we define our variable and the circular slices that we would get once the water calms down and stops sloshing around, none of that has changed either. The only thing that we want to change is the interval over which we're integrating. And we're trying to come up with the same result that we had. So what we're trying to do, so for this problem, we're going to keep the integral, we're going to keep the volume, we're going to change the interval. So we're going to keep our integral. We're going to keep the integral, we're going to keep the volume, we're only going to change the interval over which we integrate. That's the thing that we're trying to figure out. We're trying to figure out how deep the water is, and that is described by the interval over which we are integrating. Our volume, since no water was lost in the process, the volume of the water should be the same, and we're still calculating it the same way. Since we can use the same right triangle, we can use the same right triangle. So the relationship between X and R does not change. The shape of a slice does not change, still a circle at pi r squared. So that's why we can use the same integral, the same function. No water is lost in the process. That is my way of saying keep the volume from before. The only new thing is we want to change the interval. Instead of integrating from 2 to 12, that's the depth of the water is 10 feet. So we integrate from 2 to 12. Now we're going to set up an integral from 0 to question mark. So I want pi times definite integral of 144 minus x squared dx to equal the same volume, 2722.7. But now instead of integrating from 2 to 12, when the depth was 10 meters, we don't know what our depth is, but we're integrating the other part from 0 to question mark. Originally, I was going to do this one way, then another way, then another way. Now, in this case, we know what the end result of our definite integral is going to be, we're looking for what got plugged in to produce this result. Now, instead of going from 2 to 12, we're now starting at 0 and going to some unknown spot. So typically what we might want to do is include our 2600 over 3 times pi. So that we can divide out the pi and then make a cubic equation. So integrating is going to produce a cubic equation. So we're going to get 144x minus 1/3 x cubed evaluated from 0 to question mark. And I want all this times pi. And I want this to come out to 2600 over 3 pi. So the reason I switch back to this fraction is because if we can get rational numbers, since all the irrationality just comes from that pi, I'm going to divide it out. If we can get rational numbers, then we're going to be happy. We're happier with rational numbers. So let's get rid of the pi and be rational. Now I'm going to plug in the question mark. So I'm going to have 144 question mark minus 1/3 question mark cubed is equal to 2600 over 3. I didn't plug in the 0 because if we plug in 0, it's a polynomial, we'll just get 0. So when we do f of b minus f at a, we'll end up with 0. That's why I didn't bother writing that. I just wanted this cubic equation. This is a cubic equation in question mark, and no one likes it when I do this, but I didn't pick a variable. I mean, let's face it, whatever variable I would have picked is just a symbol. So we end up with this cubic equation. If we multiply out the 3, if we multiply by 3, we'll get, I'm actually going to put everything on one side. I'll have, and I'm also going to switch to an actual variables. I'm just going to use x. So we have x cubed minus 144 times 3, which I don't know, 432 x plus 2600 equals 0. So I multiplied by 3 and then put everything on one side. And now we're kind of bummed because we got this cubic equation. We got this cubic equation, and 2600 has a lot of possibilities for rational zeros. So if we wanted to try to apply some rational zero theorem to solving this equation, then we're going to have too many choices. So the thing that we notice about this equation, there are so many choices for possible rational zeros, and we did not get something that was very obviously factorable, at least not immediately. Does anybody see an obvious factoring, an obvious zero? It doesn't jump out at us. We don't see something like a cubic with 4 terms that we can obviously factor by grouping. That didn't show up. That's kind of what I was hoping for in finding this equation. So we might think we need to resort to using a machine to solving the equation. At that point, we need to stop. If I'm going to use a machine to just solve my equation, I'm not going to bother solving the equation. I'm going to go back to my definite integral, and I'm just going to start using the machine there. So instead of using a machine to solve the equation, instead of using a calculator to solve the equation, we're just going to use a calculator starting at the definite integral. We're just going to use a calculator on the definite integral. The reason that I went out and got this cubic equation was I was kind of hoping that there would be something that was very clear about what the zeros are going to be, but it didn't show up. We have a pretty good idea about what rational zeros we can pick. We're not going to bother looking for a zero where x is like 2600, because we're looking for the depth of water. We're still just going to go for things between 0 and 12. In fact, we're going to go for things for depths between 1 and less than 10. As we know, we should get a depth that's less than 10. So even the constraints of the problem give us a lot of choices. There's a few zeros that we don't have to worry about, depending on the shape of the graph. We could do more derivative analysis to find out how many turns this graph makes. Actually, that's kind of a neat question. If I take the derivative here, I get 3x squared minus 432. I spelled 4 wrong. So if I take this function, I take the derivative 3x squared minus 432, I can see that there are 2 zeros in my derivative. So I got a parabola with 2 x-intercepts. So that means that this graph must make 3 turns. Let's put all the thinking in. F prime of x is equal to 3x squared minus 432. If we set this equal to 0, we get 2 solutions. So we must have a local maximum and a local minimum like this. The problem is that we don't know where those are. We can figure out where those are, but we don't know if the number of x-intercepts are original cubic meters. Because now it depends on where those turns are, above or below. Are we looking for a zero way out here? Or are there going to be 3 zeros, or is there just going to be 1 down here? Or are there going to be 2? That would be weird, but I think that would show up. So we've decided that we're going to use a calculator to help us solve this equation. We stop and say, if I'm going to use a calculator on just the equation, why don't I just go back to the beginning where the where the definite integral first showed up and start using the calculator there. I want this definite integral to land at 2722.7. I want to get as close as I can to the 2722.7 in 3 significant figures for question mark. So here's what we're going to do. So first, I'm going to get my original value back. So I got 144 minus x squared with respect to x from 2 to 12. This is what we're aiming for. 2722.7. That's where we want to land. But we want to get there from the other direction. Instead of going from 2 to 12, I want to go from 0 to some other depth. So I'm going to start off at 0. And I'm just going to guess. Now we know that 10 is going to be, we're not surprised. I didn't want 11 though. I know it's not going to be deeper. We're not surprised that when we go for a depth of 10, we get way too much volume. We're looking for 2722.7. We got way too much because if it was 10 feet deep, including all the thin part at the rounded bottom, there's all that space at the wide part at the top that's being filled in now. So it's not going to be 10. And I'm just going to start counting down. Not going to be 8. I'm just going to keep going. I am literally just guessing now. We're getting close. And now we've surrounded it. Now we know the depth is somewhere between 6 and 7. We've got our first significant figure. It's somewhere between 6 and 7. Thinking linearly, let's split the difference. We're too low. Let's start going up. Ah, I've got it. So we're 2722.7. And now we've got it surrounded again, 2716 and 2746. That's between 6.7 and 6.8. We have got our second significant figure. It's somewhere between 6.7 and 6.8. And once again, I'm just going to use my default human thinking of linear and split the difference. 75 is high, so I'm just going to start crawling down. It's like playing The Price is Right. Oh, we've got it surrounded again. 2725.3.4 and 2722.3. So it looks like of 20, that's below. So 6.72 is below, 6.73 is above. We've got it surrounded. We just need to figure out which one is closest, and 6.72 is closest. We only needed 3 significant figures, so we just keep guessing until we get it surrounded, and then we just refine our guess from there. If someone comes along and says, 3 significant figures, I need more. And you're like, oh, dude, this is like 6.7 meters of water. And you want more significant figures? And they're like, oh, yes. That'd be like getting up in the morning and weighing yourself and saying, I am now 201.24876 pounds. It's like, oh, dude, that's a little bit more precise than you can actually be. Cut your fingernails and you will lose weight if that's how far you're going to go. But if we needed to go further, we've got the value surrounded. That's between 672 and 673. So we just keep going. That's high. That's still high. And we've got it surrounded again between 6721 and 6722. Because 6721 gave us 2722.6 and 6722 gave us 2722.9. We just need to figure out which one is closer because we've got it surrounded. If we need more digits, we just do this again. Any questions? So the point that I wanted to make here is that if we're going to use technology to help us solve a problem, just use technology to help you solve the problem. Don't use technology on a part of the problem when you could employ technology earlier. The only reason I actually integrated the function was so that I could produce a cubic equation, and that allowed me to think about cubic equations for a little bit. Any questions? If we wanted to solve this by looking at a graphing calculator, we don't need to see the actual whole graph of what's going on. We know that there's going to be a zero for this. There's going to be a zero of this function somewhere between 0 and 12. That's the one that we're looking for. And lucky us, there is only one. The next zero is way out here at past 16, and we can't have a depth of water at 16. So we just need this one. There's the 6.721. Any questions? There's our third zero. Once we saw that there were two real zeros, we knew there had to be a third one. So if we zoom out, there's the third one. But given the constraint of the problem, there's only one that matters. Any questions? Is everybody okay? These are the kinds of things that we often forget about when we're doing calculus, because we start doing calculus, we get hung up on the calculus, and we forget to remind ourselves of all the things that we still know about trigonometry and algebra and arithmetic and whatnot. So for example, we've got this cubic equation. We know that the possibilities for a cubic equation are definitely one real zero. And the context of the problem told us that there had to be one real zero between 0 and 12. But a cubic equation could have 1, 2, or 3 real zeros. Then thinking back to Calc 1, we looked at the derivative to find that there were two critical points. Since our first derivative definitely has two critical points at 432 over the square root of 432 over 3 and plus and minus the square root of 432 over 3. So we know that there are two critical points. So now we know more about the shape of the graph. Always the first derivative is not telling us where the x-axis is, but we know it has this shape this way. So there could be 2 or 3 real zeros. Knowing that there could be 1, 2, or 3 real zeros makes our life more difficult in the possible rational zero department. Because it could be the rational zero that we're looking for. It could be the rational zero that we're looking for comes from the quadratic parts. So since we're going to bring technology to bear on the problem, just go back and use technology on the original problem. And even though it's not a very good graphing calculator, the TI-84 is really good at doing these kinds of calculations. So we just want an Fn, pi, Fn int 144 minus x squared with respect to x from 0 to question mark. And we just keep plugging stuff into question mark until we get 2722.7. Any questions? Comments? Any thoughts? So let's start a preview of the next big thing. This will be the bulk of our new material from here to the end of the semester. If you recall, I like to view calculus as the rigorous study of infinity. We're trying to get a better idea of how infinity works. We're trying to get a more intuition about the concept of infinity. Because for the most part, our intuition about infinity is, without any kind of instruction, is pretty trash. So we need to, that's what calculus is about. I mean, I know technically calculus is in an engineering class, but there's a lot of interesting math stuff that goes on in calculus that we need moving forward. So the next big thing is going to be sequences, series, and power series. For those of you reading along in the book, this is in chapter 9 of the Hughes Howell textbook. Actually, even if you're not reading along in the book, this is still in chapter 9. It doesn't change what chapter it is just because you are reading or not reading. These are not Heisenberg books. I like that Heisenberg in modern can either be referring to the dude with the uncertainty principle or the dude with the blue hat. So when you bring up Heisenberg, you're not really sure which one it is, which is kind of on brand for a word like Heisenberg. Anyway, that's all beside the point. Our next big thing is going to be sequences, series, and power series. We're going to be thinking of infinity a discrete kind of infinity. This is a more discrete kind of infinity. Not discrete, we don't talk about kind of infinity, a discrete, countable kind of infinity. The infinity that we've been dealing with so far has always been about a continuum. We've been modeling a continuum with a discrete. We've been modeling this continuous sum in an integral with a discrete sum. So now we're just going to keep the discrete sum. We're going to have distinct terms, and we're going to be looking at infinity in another way. So we're going to be talking about sequences, series, and power series. Let's go over the one-word definitions of sequence, series, and power series. A sequence is just a list. A sequence is a list. So I'm just making a list of things. So S1, comma, S2, comma, S3, comma, and so on. Here's where infinity has showed up. This is going to be an infinitely long list of numbers. Could be anything we're going to use. Sequence is a list. A series is a sum. A series is a sum. Specifically, it's a sum with an infinite number of terms. A power series is a function. A power series is a function. As a variable, you can plug stuff into it. Is it really a function? That's pretty debatable. We're going for one-word definitions. They're going to leave some shit out. But a power series we're going to think of as a function. Since we are being all loosey-goosey with our definitions of things, we're going to look at power series as polynomials, but with infinite degree. Now, I know you're all looking at me. It's like, oh, if it's a polynomial, if it has infinite degree, then it's not a polynomial anymore. And that is absolutely correct. You can well actually me or actually me all day, but that's what they're going to look like. They're going to look like polynomials, but with infinite degree. That's the form that they're going to take. They're going to look like infinite degree polynomials. We're going to look at power series. We're going to start writing a polynomial and change a polynomial into a power series, which will say, keep going, keep going. So don't at me. Especially because I talked about calculus being the rigorous study of infinity, and here I'm using all this hand wavy language. So a power series will also be a sum, but there'll be a variable in it. And it'll look like an infinite degree polynomial. So it'll be something like C0 plus C1x plus C2x squared, and so on. Where C is a constant. So it looks like a polynomial. The center of this one is focused on 0. But we could have a different center. So instead of being centered around 0, we could center around any other value. So it could be a shifted version of this. Where instead of all the terms being x terms, they're all powers of x minus a. So this first one, it could just all be powers of x. The second one is all powers of x minus a. The important thing is that the variable part always has to be the same. So if I start writing a polynomial, this is not a power series. Because all the variable parts look different. For a power series, it's all got to be powers of the same expression. Questions? So right now, the only thing I'm concerned with is that we see this as just a different kind of infinity. Instead of a continuous infinity, where we have an infinite number of terms that get infinitely close together, we're cramming an infinite number of things in between two values in some continuum. We have an infinite number of distinct terms. That's the different kind of infinity that we're looking at here. The big word that we're going to have here is we're going to talk about whether a sequence or a series converges. We want to take the word converges as makes sense, gives us a value. Because we have this sum with an infinite number of terms. Does it make sense? Does this sum make sense? That is, does this infinite number of terms have some kind of value? If we add up this infinite number of terms, does it equal something? That's what we care about. The reason that we care about that is that series are going to be the result of plugging stuff into a power series. When we plug a number into a power series, we end up with a series. We want to know if that series makes sense. Does it make sense to plug this value of x into the power series? Because when I plug this value of x into the power series, I get a number. But if I plug some other value of x into the power series, I get infinity. And so in that case, it doesn't make sense. Where does it make sense, or what values of x does it make sense to plug in to a particular power series? That's the question we want to know. when we have a power series, what can we plug into it so that we get a value, something that makes sense? When you choose a value of X, plug it into your power series, which we're thinking of as a function. We're going to get a series. We want to know if that series represents a finite sum or an infinite sum. All right. This is just an overview of what we're going to be thinking about. And for those of you reading along in the book, I do like to start at the end. I do like to keep power series front and center in this discussion, because that's kind of where things are headed. All right, that's going to do it for today. That's going to do it for this week. I will see y'all on Monday, unless you show up in my office hours tomorrow, which is going to be my normal personal meeting room instead of the class meeting room. So that's it for today. That's it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.